Also today we look at the LeetCode problem, remove all adjacent duplicates in string, part 2. Given a string S, a k duplicate removes all the k adjacents and equal letters from the string. So we receive here a string, k is 2. Do we have two same characters adjacent? No, A, B, C, D. Each character appears only once adjacently. K is 3. Do we have three same characters? Yes. Here, so remove it, and here, so remove it. But note that when we remove the C's, then these B's are also 3. So there is a kind of trick here, because once you remove something, you need to re-examine. Okay, so let's look, as always, on the properties of this question before we actually start solving it, because looking at the properties of these questions would give us some big hints. So first, it's a string question. String. And because it's a string question, this means we need to pop up into our brain some string functions because most chances we'll use them. And if we don't know these functions, we should have them immediately ready for copy paste from our brain. For example, char at I. You should be able to immediately copy paste this function because it's a string function. Not necessarily in every such questions you will have this, but in okay, 2. We are going to scan the string. So let's say we have the string. How do you scan a string? For loop with the length of the string. Okay, this could appear easy for you, but I think that massaging our brains with some string functions is good. So point 3, let's take like the most basic brute force solution. So let's say I have this. Okay, the brute force solution would be simply to start scanning it. So I scan A. Oh, I have only 2 A's and now it's changing. So if I had some kind of a counter that counts the number of appearance of a character, it could just scan it, right? And now the counter would be 3 because I have 3 B's and I remove them. Question is, now that I removed it, what do I do? So in the brute force, in the naive way, I just continue, right? I just continue here and I continue, I see here another 3 and I remove them. And to be more efficient with removals, I can create a new string and just copy the new characters, non-removed characters to the new string. But once I remove this, then it looks like it's not enough to move forward. I need to look backward. So first, if I do this naive solution, which means I remove this, then I remove this, and then I need to rescan the string, and then I remove this. But since I'm rescanning the string, this means that my time complexity would be of n squared. Okay. Now the question is, let's say I'm going to improve this. How well could I improve this problem? To improve from O of n squared, we could improve to something with log of n, or to O of n, or to O of 1. O of 1 obviously is not a case. We need to do some manipulation as to traverse the whole string. So what's left is O of n and O of something with log of n. Let's see if log of n makes any sense here. Log of n usually, or it means either I am sorting with n log n. I don't see here any reason to do any sorting, or split the string in the middle or somewhere. I don't also see a reason to split the string. Okay, it's possible to split, but then you would need to combine and also traverse each side. It looks like it's making things more complicated than we need. Maybe there is an option, but it looks like it's making things more complicated. So, and therefore, I'm going to improve it I think, to often. Okay, so you see I'm starting from the complexity, and then this gives me hints about the solution. So it looks like often is possible because I would scan this, I would count here 2, and then I would count here 3 characters. And then when we said that when we have this thing that we remove this, we just need to look at how many characters of the same type of the next character we had in the previous character. That's all. This looks like often to me because I don't need to go to the beginning of the string. Okay, I just need to remove these and then to check the previous one, and I remove it, and then to check the previous one, maybe, because maybe this removal of the string caused again some strings to be coupled. I don't see, it looks like often, okay, because I'm just scanning the strings, I'm not repeating too much, and when I'm scanning the strings, I'm removing characters. This is often. Okay, let's start doing this. Let's start implementing this naive solution, this additional naive solution, where when we remove something, we look at the next character, we look at the previous character, how many times, and if the previous character is the same as the next character and appeared k minus 1 times plus this would be k, then we also remove it. And then when we remove, we look again at the previous counter and next counter. Okay. So our concept would be to remove, look at the previous counter, look at the next counter, character, and compare and see how many times it appears. Okay, let's start coding this. Okay, often. Okay, let's start coding this thing. So I'm going to have a list of string. This is the new list that I'm going to build. I'm not going to work on the original string. I'm going to create a new one. Let's call it S new array list of nothing, like this. Okay, and now let's start scanning the string. This is also a pattern where you copy the result to new something. Okay, now let's go through the for loop. For int I is starting from 0. We start from the beginning of the list. You see we had here this pattern of looping over the string. And I is less than the input string. I see the input string was a new string, new s. Okay. So until the end of the length of the string. Okay. And now let's take a look at the first character. Okay, so the first character would be s dot, and you see we already uploaded to our brain cache this function, this correct, and we upload this and we just copy paste this correct I into, and now we have the first character. Okay, so now if there is nothing in the new string, we can just append it, right? So let's append it, new string dot and then c. Okay, we are appending it if the new string is empty. If new string dot is empty. Okay, then append it. Okay, and you know I could do here an else and continue, but you see I would have too many blocks. And for simplification, although you might less prefer it, I think that using break and continue will make this even more clear, because I won't have all these nesting. Okay, this would even simplify in the coding interview how to write. So I don't like this else, not in coding interview. So we just finished. We added a new character to this thing. Let's move on to the next character. You see how it's not now much clearer? And now we said that we need to take a look at the previous item in the list, because we are now not at the first character, right? So let's say we take a look. Let's say that previously we had this, and now we are here. This is the new character, okay? This is the new, and we need to look backward. But how do we know how many D's or how many E's did we have? Because we need to go back 2 times. This is not too nice. This is not nice moving backward multiple times. So it would be better if I would store that I had 2 times E. Okay, so I'm looking backward and I'm trying to understand if I stored 2 times E. So I could have just a data structure, like each item would be an array, a data structure of how many times each character appears. So in this case, I would have this and this, okay, and this. And in this way, I only look backwards 1 slot, and I know immediately how many characters I had. And if 2 plus 1 UE is the K, then I remove them. Okay? So let's go through this. Actually, you know, because I'm looking backwards all the time and I'm adding things, which data structure, okay, let's add it to now this is, once we program it, we see that we add items to the end, we remove items from the end, right? We always push item to the end of the new data structure, and we also remove items from the end. So instead of messing with indexes, what is the last index, remove the last item, we have some data structure that would allow us to do this. Stack.push would add an item to the end, and stack.pop would remove an item from the end, right? And if you want to know how many items, what is the number at the end, we just do stack.pick. Okay, so it's better that we use a stack because we continuously look at the end of the string. Let's change this to a stack. Stack in Java is very simple. You just write here stack. Okay, and here it would be a new stack. Stack. Okay, so this stays the same, this stays the same, and here instead of add we do push. The stack is just of type string, so we need to convert because, okay, this would be string.value. We could actually make this simpler, a little bit less efficient, but simpler, okay, simpler. It would be simpler if I do here string.value of. Okay, let's see. A little bit less efficient, but simpler. Okay, so now everything is a string, not messing with characters, almost not messing. So I add this string. Okay, so let's go over it again. I have a new stack. Let's call it just a stack. Okay, I'm looping over the string. Get the current character, check if the stack is empty. If it's empty, we just push the new item. What if it's not empty? If not empty, we need to check if the last character is equal, if let's say we had this and this is the new character, B. So we need to check if the last character with the peak, this would be the last character with the peak, is equal to this character, and whether it appeared k minus 1. So that together there would be k, and we remove it. Okay, let's do this. So if stack.pick, okay, now we have it. Contains our new character and stack.pick.length let's write it like this: string last pick stack. Okay, last one. Let's write last. If last string contains C and last string dot length is equal to k minus 1, in this case this means we are at this kind of thing, because this we have a B because the last item is contains this C. Note that the last item, in our case, you will see this immediately, we actually store the two B's, as we store each sequence of items. Okay, so in this case what we do is that we need to remove it and continue. Okay, so we saw that we have this case. In our stack, just to clear up things, in our stack each items is a string in our stack. Okay, so let's say we had this, each item ends this and this. Okay, so in our stack each item is a string. So we check if the last item contains our new character, and if it contains it, what is its length? Is it k minus 1, which is 2? Yes. So remove it. Okay, and now let's say that the last character was the same, but it was not equal to k minus 1. This means we need to join this one to the last item. Okay, let's join it. So we push into the stack. So we do this. If last that contains C, yeah, okay. Now we are not at this case, so the last item is contains C. Then what we do is first stack.pop, and then let's see, stack.push, and we have the last plus C. So you see, we push into the stack BB because we removed B, and we push the last item plus the new B. Okay, and what is the last? And here also continue. And if it's a whole new item, so if all we had was in the string, in the stack was A and then B, and then arrives Z, we just push it. Okay, so this is the case that we are here now. If no need for if, stack.push C, that's it. So now we have the stack with all the removed characters, and we need to return the string. Okay, so the stack is in reverse. So let's reverse the whole thing. Okay, so when we finish with the loop, let's see, we have string builder. Again, a nice thing to remember in strings. Okay, so when we said we need to have a cache of strings, you need to have, I see, also a string builder. Okay, string builder. String, the duped, the duped is your string builder. Okay, and now we just remove everything from the stack, push it into a string, into this string builder, and it's going to be in reverse order, so we'll reverse it. So while not stack.empty is empty, what we do is the duped.append stack.pop. And now it's going to be in reverse order, so we return the duped.reverse to string. Okay. Let's run it. For sure would fail. What do you think? Okay, so it failed here. Yeah. If last items contains C and last item was the same character and the number of characters in the last item was k-1. Okay. Stack.pu is not okay. Stack.push. Okay, looks good. And now let's submit. I think it wasn't that efficient because we did not think with the string, but it looks good. Actually, it passed. Okay, so this thing has passed, and this was the solution to the problem of remove all adjacent duplicates. Let's go over again the code. Okay, one last time. We said that we saw a string problem. We needed to count the number of adjacent same characters. So immediately we popped into our brain cache some string functions such as char@, and string builder. And next we said that we need to loop through the characters to check if there are duplicates. Then we said that with a simple brute force, we just scan the string, remove counter, remove something, move on, scan, remove, move on, scan, remove, and with remove we copy to a new string. Then we needed O(n) squared time complexity because we rescan the string. Then we talked about the optimization. We said that log n does not really make sense. I don't see any reason to split it in the middle. Maybe there is some solution, but I don't see such a reason. So O(n) is probably going to be the optimization. And yes, it looks like we can scan the string. When we remove something, we just look at the previous character. That's it. The previous character. And then we implemented it. We started with an array list, but then we saw that we keep looking at the last item in the array list. We keep remove the last item. We keep add to the last item. It looks like a stack. If it works like a stack and thinks like it's a stack. So we scan to the stack. If it's just empty, edge case, just add it. We said that we prefer to use continue in order to avoid some nesting and else. Although there are some guys that don't like continue. You see, the code is not nested. Almost no indentation. This is nice, much clearer. Then we look at the last item and we see if there is any reason to remove it. There is a reason if the last item is equals to the new item that we see in the string and the last item appeared k-1 because the new one would get it to k. And then we looked if the last item is just containing the current character and it's not k-1, so we just add it to the last items. We first pop the one and then we push it. And then we finished basically with the algorithm. We just need to return the result. So we pop everything from the stack, put it inside the string. String builder is a nice thing to remember in Java. And then we reverse it because it's stack, everything was reversed. So I think this was very a good problem to look at strings and to look at how can we solve it in the reverse manner from the complexity into the solution. The complexity would give us a hint into the solution and different approaches and some stuff to remember in your cache. So thank you guys. Let me know what you think and see you next time.